Hello and good afternoon. Let me turn my video on, scare all of you. If you can handle this, you can certainly handle business calculus. So let's get with it here. Oh, here we go. Okay, so you can see my office behind me. I'm at home, of course. And what you might not expect is that I'm not all dressed up, because as soon as I'm finished, I'm headed out for the roads. What roads? Well, I've spent a lot of time running in the past, and that's what I hope to do today, some running and some walking. Hopefully a lot of fun. Today, though, we are going to talk about functions. And the first thing I want to do is make sure that my pen is running. Okay, we're in good shape. Let's see, let's make something good about this. Make that an exclamation point because we are talking about calculus. And let's put a little smile on that guy. So, that's the first thing you need to do to learn calculus. Put a smile on your face. Next, here are some of the things we're going to talk about. And if you want to really read those, write them down, go ahead. It's up to you. But I'm just going to move on. Functions. You should have heard about them before, but I'm going to assume that you've had a mini case of calculus Alzheimer's. So maybe you don't quite remember. Well, we've got an example here, and this has to do with total revenue. Excuse me, I usually have to find where my pen is. Total revenue is usually represented by a capital letter M, at least in my experience, and that's relatively small. And that revenue, you have to keep in mind, is how much money is coming in to your business. That's before you pay the bills. And if you've got a typical business, we're going to keep it real simple. Let's suppose you sell pens or something. It doesn't matter what it is. Make up something that makes sense to you. Anyway, what we're going to do is whatever those things are, we're going to say we're selling X units of them. And for some of you, that might be 100, might be 152, whatever it is. X represents that in the, well, it does anyway. So each one of those items, whatever you decide you're going to sell for $1.25 per unit. Now before we go on, notice that there was an extra line there. Sometimes this pen or something in the works creates extra lines, so just be aware of that. It's not me doing something crazy, it's the computer doing something crazy. Anyway, so we're going to sell X units of something, and we're going to sell them for $1.25 for each one of them. The revenue, the total revenue, can be calculated. There we get some of those extra lines again. The revenue can be calculated by multiplying 1.25, which represents $1.25, times how many of the items, X in this case. So a few examples might help if you're not familiar with it. Throw some numbers in X and see what happens. So if you sell 10 of those items, how much do you have coming into your cash register or whatever it is? $12.50. Just multiply the number of items times the price per item, and you get the revenue for that particular day or hour or whatever it is. So let's get to a function. The R that ends up being at the end of the rainbow, so to speak, is the dependent variable. And we call it a dependent variable because it's going to be different depending on what you choose for x, how many items you have. X is the independent variable because in theory you could pick any value you wanted for x. But once you pick that value for x, r is totally locked in, and it's locked in by that function or that equation. So here's the definition of a function. See, here we go. Definition of a function. There you go, the extra lines again. Function is a relationship between two variables that says each value of the independent variable, that's x, for every x, you get exactly one value of the dependent variable, y. Pick an x, you get exactly one y back for your money. You don't have to be too concerned about this, but we do talk about it occasionally. The domain is all the possible x's that you can think of, all the legal x's that you're allowed to use. The range is all the y values that you could get by using the numbers from that first set. Take the first set, use that function or that equation. It calculates the item that's the y value or in the range. If you take all the possible answers you can get for y, it makes up the range. That's pretty much what it represents. You can think of it in terms of a machine. The x that you pick is only, if we're talking about numbers, it's only certain numbers. In some cases, for example, it might be only positive numbers or only non-negative numbers. If, for example, x represents the number, let's suppose we say we're selling pens. X represents the number of pens. Well, if you give it a little bit of thought, you can't just use any x for that. You can't have a -5 pens. What would that look like? You could have 0 pens. You could have 17 pens, 18 pens. So a -5, no. Also, 17.85 pens, can't do that either. So in this case, the domain, if we're using pens as an example, the domain would include all the non-negative integers. So 0, 1, 2, 3, 4, and so on. It'll depend on what the situation is, what the scenario is, what your domain is. What x's can you really pick? What numbers can you really pick for the x? So once you pick an x, you dump it into the machine in the hopper at the top. Inside the machine, some calculations are done. For example, you start with the x, maybe you multiply by a 3. Maybe after you multiply by 3, you add 15 at the end. That might be what's going on inside this machine. So you drop the x in, some calculations happen, and something comes out the other side. So if I took, for example, if I let x equals 2, I drop it in the top of the hopper. Inside the machine, it's going to take that 2, it's going to multiply by 3, that'll give it a 6, add the 15 at the end, and what you'll see come out at the other end is a 21. So maybe this 2 would represent 2 of whatever you're selling. The 21 would represent how many dollars come into your cash register. That's sort of how it works. All the possible x's put together as a lump create a set called the domain. All the possible things you could see coming out at the other end, if you lump those all together into a set, that makes up the range. That's what we're talking about. Next, here's an equation. Y is a function of x. That means once you choose x, it's going to go through some number process. Here's the number process in this case. When it's finished calculating, you get a y. Remember, this is the independent variable, and this is the dependent variable. You choose the x. Once you choose the x, the function tells you how you find the y. Next, how do you decide whether you've got a function or not? Because just because you throw x and y's together doesn't mean you've got a function. That's not necessarily so. In fact, take a look back here for a second. We have y equals 4x squared plus 3. All we had to do is throw in an x, you find the y. Keep that in mind. If we look over here at the first one, it helps to see if you can put that like this, where it's 1y equals on the left side and some expression about x on the right side. So if I take this equation, I want to change it so it looks like this. And the box, we don't know yet. Well, how do you do that? Well, in this particular case, where's my cursor? There it is. To get this y all by itself, all I have to do is subtract x from both sides. So I'll subtract x from both sides, and I'll have y equals minus x plus 1. There's your function. If you can write it that way, you've got a function. What am I saying? I'm saying that if you can take whatever your equation is and you can write it as, sorry about that, if you can write as 1y equals some expression with an x somewhere in it, you've got a function. Think of it in terms of a calculator. If I put a certain number in the calculator, we'll call this a calculator. We'll give it a small screen here, and it's got some buttons for you to punch. Put the x in. You tell the calculator how you want this thing worked on, and out the other side comes 1y. That makes it a function. In fact, calculators are basically function machines. Put a number in, the x on one side, or in, you know how to put it in, and what you get on the screen is one answer. That makes it a function. So you're thinking maybe, well, as long as I have x's and y's in an equation, I've got a function. Well, take a look at the second one. The second one is x squared plus y squared equals 1. So let's see if we can do that. Well, here's the y. This is the only y variable here. So we're going to get rid of the x squared. So we'll subtract x squared from both sides. That'll give us y squared equals minus x squared plus 1. So far, so good. You might jump to the conclusion, hey, that's a function. Not quite so fast. You do have a 1 in front of the y squared, but you don't have a y. You have a y squared. We want a y out here, not a y squared. So we'll have to take the square root of both sides. That doesn't sound too bad. So take the square root of the left side, we've got a y. The other side, we'll take the square root of this. Let's see if I can write it again. Y equals square root of minus x squared plus 1. Looks like we're done, except for one thing. Whatever this number is, if this is a 7, for example, to get the y squared up here, we could have had a negative 7 there. So when we take the square root, we have to remember that there are two possible answers here. That ruins it for being a function, because the idea is you take an x and you perform some function on it, and you end up with only a single y. Well, we've ended up with two y's, a positive value and a negative value, not a function. Third one. Well, looking at the last one, you think, oh no, this looks scary. We've got squares there. Let's see what happens. There's the y. We want the x squared gone from this side so we can have y equals. So we'll subtract x squared from both sides, and that'll give us y equals minus x squared plus the 1 that's already there. Notice that this is 1, that's good, and this is just y. It's not y squared or y cubed or anything else. We've got it. If you think of it again in terms of the calculator, put any number in you like for x squared, how many answers will we get? One answer. Take any number, square it, take the opposite, add 1 to the final, and you'll get one answer. This one over here was a function. We'll give it an F, but that's a good thing in this case. This one's not a function, and this one gets the seal of approval from the function god. Last one, let's see what happens here. I want the y by itself, so I'll subtract the x from both sides. That'll give me y squared equals minus x plus 1. Uh-oh, I've got a y squared. I need this in terms of y for it to be a function. So I take the square root, y equals the square root of minus x plus 1. But because I'm taking the square root, this original number could have been a plus or it could have been a minus. That means I get not only one value for y, but two values for y. This is not a function. Two values for the price of one, that's not a good thing. That's like walking in a store and picking out a sweater that we want to buy. And you go up to one of the clerks and say, oh, I don't see a tag on this. What's the price on this? And they say, oh, $18. And just to make sure it's $18, you walk up to another clerk and you say, how much is the price on this sweater? And they say, oh, that's $75. Well, that's sort of strange. You expect pricing to be a function. Check out a sweater, one price, not two prices. That's pretty silly. Well, that's one silly way of looking at a function, but that's how it goes. Summed up, start with any x from the domain. Once you've chosen your x, you're only going to get a single y or a unique y for your answer. Unique y. Moving along. just want to get past this because we already did that. You can look over the slides if you want to on your own and see if you can guess which way each one goes. Here's a picture of some other expressions. Now, if you take x's and y's and put together an equation, you don't necessarily, as you've seen, have a function. But what you do have is something called a relation. Sorry about the extra lines. If you can read through that, as long as you take x and y's, put them in an equation, squares, whatever you want to, you have a relation. It just tells you what the connection is between the x's and the y's. How you can pick ordered pairs. So in this first one, this should look a little bit familiar. This is a function. Every x you pick, notice the x's are on this axis, of course, the horizontal axis. No matter where you go on this axis, wherever you stop, and you go up to the line or curve or whatever it is, how many y's do you get? So in this case, no matter where you go along here, if I stop here, for example, go toward my curve, there's only one y value. If I go over here, this x value has only one y value. This one is a function, and if you go by what I showed you earlier, you can change this into 1y equals an expression, and you're fine. So it's a function. Second one, another way of deciding whether it's a function, if you have the graph, which we have on these four, if you can draw a vertical line, like this, if you can draw a vertical line anywhere, well, that wasn't nice, come on, pen. If you can draw a vertical line, imagine that's vertical, it's a little bit messy. If that vertical line crosses your graph at one point, good. But if you can ever draw a vertical line that crosses two or more times, it's not a function. In this case, we can draw a line right here. Sorry, I'm not very good at this. This x value from right here gives us two different y values. This is not a function. Function, not a function. In this one, imagine that you're starting on this side. Imagine you're reading this function and you're sliding a vertical line left to right. Well, that vertical line, looking more like a vertical line, does it ever cross the graph at more than one point at a time? Well, I can draw this one, for example, if I can draw a better one. I don't know why I'm not doing too well on this. Try this. Draw that vertical line, it crosses it once. If I move it over here further, it'll never cross more than once. If I move it back here, it'll never cross more than once. So if you have a graph of a possible function, a relation, we can give it the vertical line test. If any vertical line you draw only crosses your axis at exactly one point or less, then it's a function. If it crosses two or more times with any vertical line, it's not a function. An example is this fourth one. By the way, this was a function because You never find the vertical line that crosses it twice or more. On this one, however, it's easy to draw a vertical line. Oops, why is this doing this to me? I guess because it's because I have my hand on the graph. You can draw a vertical line. Imagine that's a vertical line. Anyway, and it crosses it twice. Disqualified right there. All you have to do is be able to cross a vertical line twice or more, and it's not a function. Function here, not a function there, function, not a function. Moving along. Domain and range. I've explained that a little bit already. The domain, if you lump all the possible x's together and put those in a set, that's the domain. If you take all the possible output, or all the possible y's, all those put together into a set make up the range of a function. Now, to keep it as simple as possible, usually what that amounts to is, when you're trying, the domain means what x's can I use? Can I use a 17? Can I use a -3? What can I use? Most of the times, what you need to do is set your eyes on the denominator, if there's a denominator. If that denominator, if this has x's in the denominator, if the denominator only has a 5 or an 18 or 96 or pi or something like that, don't worry about it. You can use any real number at all. But notice that this has an x squared in the denominator. So red flag goes up for you. And what you can do to make things real simple is take that denominator and set that equal to 0. The reason for that is that this denominator can't be 0. If you try it on your calculator, just for example, 1 divided by 0, you can't do that. You get an error. You can't divide by 0. So what this does is lots of these x's will work from the real number line. If you put a 5 in there, you can get an answer. If you put a 3,000 in there, you can get an answer. But we want to make sure this doesn't ever happen. So set the denominator, if it has an x, equal to 0. Solve that equation. And these will be the x's that you can't use. Remember, it's not the x's you can or that you're looking for. Those are the x's you have to avoid. I wrote it twice, but that's okay. So we're solving basically a quadratic. The easiest way to do that is factor that quadratic. This happens to be a difference of squares. That's how you factor it. It's supposed to be an x minus 2 times an x plus 2 equals 0. Set each one of those factors equal to 0. Keep my fingers crossed here. Get two simpler equations. And I get 2 here. And I get a -2 there. Now that doesn't mean 2 and -2 are the domain. What that means is more like this. Let's start again. We're looking for the domain. And if you want to write down the domain, there's a couple ways I would suggest. First of all, usually you can use a lot of the real numbers, a lot of them. So typically, you'll start by describing your domain as the real numbers, but we found out that 2 and -2 can't be used because they'll give us 1 over 0. So for the domain, we'll say the real numbers except x equals 2 or -2. There's another way of describing it that I saw years ago, and I really like it. It's up to you though. Sometimes the real number set is represented by a fancy R. Now this other way of describing the same situation is the domain equals the set of all real numbers, and this minus sign says except for what follows in this set. That's a second way of putting it. Another way of putting it would be with intervals. Now if you go back up here, we're talking about the real numbers, that's all the numbers on the x-axis, for example, the real number line, except for 2 and -2. So if you're going to graph it, you'd fill in the whole number line, but you'd erase 2 and -2. So picture-wise, it looks a little bit like this. There's the 0. There's -infinity out in that direction, positive infinity in this direction. At where the 2 is, you'd have a hole. At -2, you would have a hole. The rest of this, if I can do this without the graphics tablet screwing it up, you have everything up to the -2. You have everything between -2 and 2, and then everything after the +2. I think you need to draw your own picture. This doesn't look real nice at all. A better way of describing it, you don't have to worry about the pictures, is if you look at this picture right here, we've basically split the number line into 3 sections. We've got a section from -infinity up to -2, not including the -2, so we'll put parentheses there. Plus, we use a set union for this one. The second area is from -2 up to 2, everything in there. And we've got a third set, we'll use set union again, and this includes everything after the 2 up toward infinity. Clean it up and you've got a good example there. So lots of ways of describing what the domain is. Remember, it's all the x's that you're allowed to use from the real numbers. So here are a couple examples. The first one I would say is sort of the better one. So we'll start with that one. So if I start down here and I'm going to rewrite this. Now remember, we want the domain, we'll worry about the range in a minute. What's the domain? The domain is what x's can you use? Well, it looks like it's okay. Put any x in, subtract 1, take the square root. Oh, wait a minute. We have to make sure this doesn't end up being negative. If I took x minus 1 and I got a -6, I can't take the square root of that and get a real number. So I have to be a little bit careful. What does careful mean? Careful means what's inside the square root can't be negative. Put in other terms, if it can't be negative, that means it can be positive or it could be equal to 0. Anything other than that, and you're not going to be able to find the square root. Now, this doesn't tell us about the x's exactly. It's talking about x minus 1. So we'll have to solve this one. Add 1 to both sides. There's our domain. That's good for number 1a, or just a, I guess. The second one is a little, well, let's take the range while we're at it. What numbers could you expect to get from, where am I? What numbers would you get out of this? We could get 0, really. Notice there's no minus sign out front here. No minus sign. So everything is either going to be 0 or it's going to be positive. Sort of like that. So we can have 0. If we use the interval notation, 0 is included, so we have a bracket there. And there is no biggest number that we could get out of that square root. There's your range. If you want a quick picture, here we go. If you've got a number line, 0 is an important point here. So 0 is included, and everything to the right is included. There'll be a graphical interpretation of what we've got. Okay, let's tackle the other one. So let's start with the domain. Right here on the right-hand side, it tells you what x's you can use. See if I can carefully rewrite this. This tells us which x's we can use. Well, that doesn't leave anything out. So the domain includes everything less than 1, okay, and everything equal to 1, and everything greater than 1. That's everything. So up here, for the second function, we have all real numbers. You can write it out, or you can do it like this if you like. Now, how about the range? We're going to have to look at this in 2 parts. First part, for numbers are less than 1, this is how we're going to calculate the y value. Well, what does that give me? Well, I don't use a 1 there, but I could have, for example, and you can play around with this. That's the best way to do it. Play around with it. So if I used a 0, 0 is allowable. If I use a 0, in fact, you might make just a table of values just to get an idea of what's happening. If I used a 0 in here, I'd have 1 minus 0 would be 1. If I put a minus 1 there, put a minus 1 in here, I'll have 1 minus a negative 1, or 1 plus 1, negative 1 gets paired with a 2. If I try a negative 2, Put that number in here. 1 minus a negative 2 is 1 plus 2. Negative 2, 3. Negative 3, try that. 4. So you can get an idea what's happening. Well, we missed a few. How about something a little bit closer to that 1? Let's extend this. Sorry. I'll draw another one. I'm going to get a little bit closer to the 1 to see what's happening, to make sure that what I think is happening is actually happening. So let's say we've got, where am I? Let's get real close to that 1. Let's make this 0.9. That's still less than 1. When I put the 0.9 in, I'll have 1 minus 0.9 is 0.1. Well, that looks interesting. What if I get a little bit closer? 0.99 is even closer to the 1, but it's still less than 1. Put that 0.99 in here, I get 0.01. If I put a 0.9999, subtract that from 1, I get 0.0001. In other words, what's happening? That thing is getting closer to 0. So what does the range look like for this one? The range for this part of it, where am I? There we go. The range for this part of it, I can't use the 1, but when I get something close to it, it's almost 0. Almost 0. So that's where the range starts for this first part. And if I look down here, what's happening is I use the negative numbers. I get bigger and bigger numbers. I expect that to continue. So for the first part, the range is 0 to infinity. That's part 1 of part B. How about the second part? I'm running out of space here, but let's see what we can do. The second part says we're going to take the square root of x minus 1 when we have an x that's either 1 or bigger. So let's play with it. So some x values, some y values. Now for this part of it, we're allowed to use the 1. So let's see what happens. If I put a 1 in here, I get the square root of 0. 0. That's simple. Keep on going. X's are bigger than 1. See what happens with a 2. Put a 2 in there. Square root of 2 minus 1 is the square root of 1. It's 1. Now, I want to be a little bit clever about these x's that I'm picking. Now, you could just use your calculator and use a 3, 4, 5, 6. But since I'm doing this on the fly without a calculator, I'm not going to use my calculator. I'm going to pick x's so the square root comes out even. So what I'm going to try is I'm going to try putting a 5 in for x. 5 minus 1 is 4. Square root of that, I get a 2. If I put a 10 here, 10 minus 1 is 9. Square root of that is 3. If I put 17 in there, 17 minus 1 is 16. Square root of that is 4. Can you see what's happening? If I put 101 in for x, what do I get? 101 minus 1 is 100. Square root of that, 10. if I put this number in, subtract 1, take the square root, I've got 1,000. I think you can see what's happening. At the lower end, I have 0. At the top end, infinity. So for the second part, the range starts at 0 because it's exactly 0, and goes to positive infinity. Now we want the range, all the y's that could come out of this thing. So what we want is these two thrown into the bucket together. Well, they're almost the same thing. 0 to infinity, 0 to infinity. The only difference is that this one includes 0, this one doesn't. When we throw them into the bucket together, I end up with that 0 that I got from the second one, and there is no upper limit. So there's the range for the function in B. I would ask you for a question, but you were just watching this on video. So moving along, let's see. All right, and this gives you a picture of what's going on. Honestly, it's a really good idea to use your calculator and get a picture of what's happening. Taking a look at that square root of x minus 1, you can see what's happening. You get x values from 1 on up, y values from 0 on up. Piecewise one, that's what it looks like if you graph it. Remember, there are two parts to it. The part from less than 1 and the part from 1 on upward. The two parts, the two pieces, look very different. They do have one point in common, well, almost in common in the middle. This one approaches is 0, and this one actually starts with 0 and takes off. Next, so far we've talked about a function. Now we're going to take it one step further. A relation is a set of all ordered pairs you can dream of, anything at all. The function is, when you take an x, it's paired with exactly one y value. But if you took those ordered pairs and reversed them, you might not always have a function. But sometimes you do. If you took all those ordered pairs and just flipped them, what do I mean flip them? Let's suppose just one of the ordered pairs in your function was the point 2,5. What about 5,2? If I took all of the ordered pairs in that function and flipped every one of them left for the right, would I still have a function? Usually not. If I do, it's called a one-to-one function. Remember too that you can look at a graph of a function and you can tell it's a function because it passes the vertical line test. It never crosses the graph at more than one point for any particular vertical line. Well, 1 to 1, you've already given it the function test with a vertical line. To decide whether it's 1 to 1, you give it a second test, the horizontal line test. If you can slide a horizontal line top to bottom, bottom to top, and it never crosses the function more than once, you got a 1 to 1 function. In some respects, you might think of this as a superfunction. It's not only a function forwards, but it's a function backwards. In fact, we're going to get to that in a few minutes. First, some notation for functions. So here is a function. You can recognize that fact right away, even before graphing it, because you have 1y equals, and then some expression involving an x, possibly. Function. If you graph it, run the vertical line test on it visually, you can see that it never crosses more than once for any vertical line. Now, another way of writing the same thing is taking your equation and replacing the y with this notation instead. Instead of writing it y, you write f of x, it's called. Now, there are two things involved here. First of all, the x in here just means this is the variable I'm using. The f means, what am I calling the function? It's a name. For example, let's suppose your name is David. Maybe you'd like this to be clearer. Maybe you'd like to call it David of X. That's perfectly valid. You could call it Charlotte of X, anything you like. The F is just a name, nothing more. It definitely does not mean that F is multiplied times X. It means F is the name of the function, X is the variable you're using. Second, here's our function. Let's write this again. Hopefully no straight lines like that. Yikes. There's our function, minus those terrible lines that drive me crazy. And that's the definition. Now, what does that mean? Okay, the f tells you which function we're talking about. This number right here says, what number are we going to feed in to the function? We're going to feed in a 3. So everywhere you see an x, you're going to put a 3. Evaluate it, and there's your value. Squeezed a little bit. The function value for 3, if you put a 3 in your function machine, what do you get for an answer? -1. That's what it means. This is the number you're feeding into the function. This is the name of the function. It also means something else too. It means that since this 3 is the x value, that for that function, one of the ordered pairs has an x of 3, and this f of 3 says, well, when I put a 3 in, what do I get? The 3 is paired with a -1. This is how you find out what the ordered pair is, or one of the ordered pairs. Another way of writing the same thing is for that f of x. I give up on that one. For 3, how do I get the second coordinate? I send it to f and see what he sends back to me. Next. Okay, we're getting a little bit more interesting. So what is this thing? Okay, first of all, we're going to start with this triangle X thing. That is delta X. This triangle thing is a Greek letter delta. In fact, if you're keeping track, it's a capital delta. Now, why am I putting that there? Because this delta is sort of a shorthand for the word change. When we write delta x, we're talking about when we're graphing something. I'll just go ahead and use that. If we're graphing something on the xy plane, and we've got 2 points. If I were traveling from point 1 to point 2, how would my x value change when I went from 1 to 2? It's going to change by that much. That's my delta x. When I'm traveling from this town to this town, how far east or west am I going? By the same token, you could say something about how the y value changes. That would be how far north or south we were going when we went from town 1 to town number 2. So that's what delta means. So f, see if I can squeeze it in up here, f of x plus delta x. What's that mean? It means that we're talking about a particular place on the graph. If we sneak back earlier, maybe x is a 3, for example. And we want something very close to that 3. So we'll add a very, very small positive number to that. Maybe this x plus delta x is 3.001. This 0.001 is the delta x. It's just a little bit bigger than the x we started with. That's what it represents. Now here's a sidebar for you. The delta x can look too much like delta times x, obviously. There's another notation that is also used that I prefer to use because I like as little confusion as possible. Instead of using delta x, I prefer to use an h. H and delta x. Let me try one more time. They're the same thing. It's a small positive number, as small as possible, really. A positive number. So this x plus h, the f of x plus h, is the function value at something real close to the function value for x. So if you were down here it would be, this one would have a y value of f of x. This one would have a y value, f of x plus, I'm going to use the h there instead of delta x. So to throw in one last example for part A, if I use real numbers in there, excuse the pun, this would tell us what number was paired with 3. And if I add just a tiny bit to that 3, this 0.0001 is your delta x or your h. This would tell you what y value was paired with 3.0001. 3.0001 and whatever that turned out to be when you put in the function. You can do that yourself. Put the 3, where am I? Put the 3 in here, square it, add 7, you get a y value. Put the 3.0001 in there for x, square it, add 7, you get the second y value. That's how that works. Now let's move on to part B. That looks a little bit confusing. It is confusing. I'm going to rewrite that using that h that I showed you earlier. The same thing can be written as f instead of delta x. I put an h there. You'll want to rewrite this. Notice that this x plus h and this x are very close to each other, but they're not the same. Notice also we're subtracting them. That means we're going to get a difference. On the bottom, we've got h, a very small number. It's the same h that we have up above. Now where did the h come from? Well, that's sort of sneaky because someone actually did a little bit of work ahead of time. So what we've got here is these are y values. We're subtracting the y values. Now why do we have h in the bottom? Well, if you remember slope, remember slope? We have y2 minus y1 over x2 minus x1. Okay, so this top looks like you're subtracting the y values like with the slope. Well, on the bottom, if we look at the 2x values, what 2x values did we have on the top? We actually had x plus h, and we had an x. But if I take this fraction and do the simple subtraction in the bottom, which I can do, I have f of x plus h, same thing, f of x. But when I subtract in the bottom, the x's cancel out, or give me 0, you now have h. That's where the h comes from. Sneaky, but it is. Notice, be very careful. Let's see, what can I do here? Okay, this guy's a little bit scared because you might consider doing this. You can't subtract these and get f of h, because this expression right here means you have to add the x and the h first, give it to the f function, and it's going to do its thing. Over here, this says take the x value, give it to the f function, it'll do its thing. These are the results of giving x plus h to the function f. This is the result of giving x to the function f. We don't know what those values are yet, so we have to leave it like this, but we can subtract on the bottom and we just have h. So you might want to use this anytime you see that. I like it so much that you're probably going to see me use the h almost all the time instead of delta x. So, final reminder, this delta x is not delta times x. Not. If you wrote this properly, it should be delta x in parentheses, frankly. Okay, we've got to move on or we'll be here forever. I know it seems like we've been here forever already. Okay, so this says the result of part A, you can write this. Okay, what we did was, remember our function, because this wasn't carried over here, our original function f is x squared plus 7. Now, you're going to see this notation often. The thing to keep in mind is that if you look at this as if you were a second or third grader, for example, on the top, you've got subtraction. And when you subtract, your answer is called a difference. The fraction bar means division. What do we get when we finish our division? We get a quotient. So what we'll end up with is a difference quotient. That difference quotient is going to be very important because that's going to give us our calculus. And just a heads up, we're going to do some nasty things for a while, or you're going to think of them as nasty, and then we're going to find some shortcuts to enable us to find difference quotients faster. Now, what's going on here? I haven't really gotten to that yet. So if I want to work with this, how do you do that? Remember early, just a few minutes ago I said, well, let's go up here to the easy part. This is the original function itself. If you look over here, there's my original function. It's just copy and paste, nothing more. The second part is a little bit more tricky. This means you take x plus delta x, or x plus h, and you're going to give it to f. Now what does f do? Let's see if I can write this better. Function f says you're squaring whatever you get and adding a 7 at the end. This says that what you're going to give f, what Mr. f, the function, is going to see is x plus delta x. Here's a trick that I always use. So you want to find out what this difference quotient is. So what I suggest is this. First of all, you want a difference quotient. So you're going to be subtracting some things. And down the bottom, I'll leave the delta x there for the time being instead of h to keep from confusing you. Now, what do I put in? Okay, let's start with the easy part first. The second part says f of x. Well, that's easy. We'll just take that x squared plus 7, copy it right in there. Just copy. Do nothing. Just put in the second set of parentheses. Now, the part that might be confusing is what do I do with that first part? It looks like a total mess. Well, here's what you do. My function, if I can write it properly, your function is actually telling you this. You're going to square something and you're going to add 7. So that's what we'll do in here. We're going to square something and add 7. That's what the function says, x squared plus 7. X to be sent to you later. What we've been sent, though, is something called x plus delta x. So I'll put in x plus delta x. And that's it. Write the function with empty parentheses for the x's. Whatever this says here, put that into the blanks. The rest is mechanical and making sure you don't make silly mistakes. So where do we go from here? Okay, first of all, we're going to take the easy part first. We're subtracting x squared plus 7. The minus is going to go across here. We'll have minus x squared minus 7. That's easy. Make sure you put the minus on both of them, or rather, change the sign of both of them. Now, the first part. Now let's do the other easy part. On the bottom, we'll just have delta x. Remember, that's one number, not two. On the top, again, let's go with the easy part first. We've got 7 there, plus 7. This is killing me. Let me see if I can rewrite this for the time being. So, here's the 7 that I just put there, and the minus x squared minus 7 that I have here, and the delta x down there. Okay, we've got the simple parts done. Now the next thing is, up here, there we go. Here's the sticky part. X plus delta x, I'm supposed to square that thing. That's one reason why I like using h instead of delta x. But we're going to do this one time with the delta x. So up here, that's what we're trying to do. If you need to, remember that means x plus delta x times x plus delta x. What's that going to give us? It's multiplying two binomials, which in this case are identical. You take the x times the x. I'm going to bring it down here because I know I'm going to get an x squared when I multiply this times this. I'm going to skip ahead for a second. I am also going to have to multiply delta x times delta x. And that's going to give me, and I'm going to have to use parentheses for this one, delta x squared. Whatever that represents, don't worry about it. Now, I've got something in the middle, because when I'm multiplying binomials like this, I'm multiplying those two together, and I'm also multiplying those two together. That might remind you of FOIL. That's exactly what we're doing. First times first, that was the x squared. Last time last is the delta x squared. And I've got the outside and the inside, and they happen to be the same thing. Both of those are going to give me x, delta x. Since I've got two of them, then down here I'll have 2. I hope this doesn't mess up for me. Yeah, that's what I've got. Go back through that, make sure that you can do that all right. If you want to, you might take what I'm going to do in the future and just put an h instead where the delta x's are. Okay, let's see where I've got. So I'm going to take this and I'm going to figure out what I've actually got. So my difference quotient, what's on the bottom? I've still got delta x. Nice and simple. Now let's take a look at the top. Here's where it would be handy to have a different color, but this thing doesn't want me to change colors. If we take a look at the x squared right here, put an asterisk above it, I've got a minus x squared over here. So when I put those together, I'm going to get 0. Also, I've got a 7 here and a minus 7 there. Total, 0. So what's left? All 4 of those terms are gone. So this shrinks real fast, which should bring joy to your heart, a little bit anyway. So what do we have? And let's keep my fingers crossed. What do I've got left is 2x delta x, and I've also got the delta x squared. Getting closer. Looks like it's almost finished, but it's not quite. I'm dividing all this by delta x, so divide delta x into both of them. If I divide delta x in the first one, the delta x is going to cancel. Gives me 2x. Hey, not so bad. In the second part, I've got delta x down here into delta x squared, which means this delta x is going to cancel one of those delta x's. And there's my answer. Let me try that again. 2x plus delta x is our answer after all that. Okay, let's keep going. We went through all that. Combinations of functions. Now things get easy for a while. I know this is getting long, so hit the pause button, go get something to eat or drink or whatever, come back, start up again. Not at the beginning. Okay, so the way I sometimes describe this is someone gave you some functions, and you think, gee, these functions are pretty nice, but I'd like one of my very own. Now, if you're someone that likes clothes that are made by designers, why not design your own function? So let's suppose this function was made by Frank. He put an F there because It's Frank's function. Frank's function says 2x minus 3. In other words, when you get an x, multiply by 2, subtract 3, and you get the y value. George gave us this function. George's function squares x and adds 1 at the end. Well, that's nice for Frank and George, but I want to make one of my own. I'm a unique person. I should have my own function. So what I'm going to do is I'm going to create a new function. Where am I here? Oh, there we go. I'm going to make my new function real easy. I'm going to take Frank function, add it to the George function, and all I need to do is just add the individual definitions and simplify. I've got 2x minus 3 plus x squared plus 1. Just do a little bit of algebra. There is my function. And since my name is Dale, I'm going to call this d of x maybe. D of x is x squared plus 2x minus 2. Bingo. If you're single, all the girls will be after you because you've got your own function. But maybe someone's already taken that one. Doggone. Well, there's another way you can create your own function. Another way is you could subtract those functions. You could take the Frank function, subtract the George function, do a little bit of algebra, and here is the Frank minus George function. Since I've already used e, I'll just call this e of x maybe. E of x equals minus x squared plus 2x minus 4. Great. Another designer function. Maybe someone's taken that, so you think, okay, what can I do? Well, I could multiply George function by the Frank function and just do a little bit of algebra. 2x times x squared, 2x times 1, then minus 3 times x squared, and minus 3 times 1. There is my Frank times George function. Maybe you'd like to call that, well, we can't call it f of x. Let's jump somewhere else. Let's say maybe m of x. Whatever you want to choose. Or another possibility is take those two functions from Frank and George and take the Frank function divided by the George function. Put the Frank function on top, George function on bottom, you got it. And maybe you call this z of x. Here's your new function. The last one has a small catch sometimes attached to it. Notice that in this one, you've got a denominator that has an x in it. So that would give you a little bit of a concern because of the domain. You have to make sure that doesn't be 0. It doesn't happen to be 0. So we'll do a quick check here just because we've talked about this a few minutes ago. Start again. Start again. I'm going to keep on going. So this would tell me which numbers I don't want to use. Let's see what happens. So this gives me x squared equals negative 1. And if I take the square root of both sides, I'll get plus or minus because I get two answers. Square root of negative 1. And the square root of negative 1 might look familiar to some of you. Let's see if I can rewrite this without having it screw up on me. There is no square root of negative 1 in the real numbers. Both of these possible solutions are not solutions in the real numbers. That means that we don't have any numbers we have to throw out. We can use any real number we like, and we're fine for the domain. If we take a second look at this, we might say, oh, I should have figured that out. Because as far as x's are concerned, I can square any x, add 1 to the end, and I never end up with 0, because this x squared is either 0 or positive. Add another 1, I've got another positive number. So your domain will be all real numbers. I'm okay. The other ones, because they end up being polynomials, polynomials use any real number at all. So we didn't have to worry about those. It's only when we have an x in the denominator that we have to be a little bit concerned. Moving on. Now, adding two functions together, subtracting two functions, and so on, isn't enough. There's another possibility, and we're going to use this in the future, so don't discount this as something exotic that you're never going to see again. We are. This is putting a function inside a function. Now, imagine, if I can draw these, we've got some offices. For function f, we're going to say this is the office for Frank, and this is the office for George. You know how they work. F of x. This is how Frank works. You give him a number, he squares it, and hands the paper back to you with a squared answer. If you take a number to Mr. George, he takes the number, adds 1 to it, he's not finished, then he squares it and hands that back to you. The question is, what if you go to Mr. F with a number? He hands you back a piece of paper with a result, and instead of going back to your desk, you go over to Mr. G and hand the answer to him. He does his thing. Oh, that's interesting. You have two functions working like that. Start with one, take the answer to the second one, and get a final answer from the second one. But you know, there's a second way you could do that. What if you started with Mr. G? What if you went there first and then went to Mr. F? You might think that you'd end up with the same answer. You might be wrong too. Now what we're talking about here, if we look at, there we go. So what does this mean? Notice we've got an inside function and an outside function. We've got the x. That's the number that we're going to give to G. So if we want to find out what f of g of x is, we're going to take the number, run it through G. When we're finished, then we're going to give it to f. Oops. This wasn't x plus 1 squared down here. My mistake. So how does this work? First of all, work from the inside out. So f, while you're working with Mr. G, he takes a break, takes a coffee break. What does G do? Well, he looks at that x, and G takes whatever he gets, adds 1 to it. So the result of x plus 1 is what the f function is going to see. Now what does the f function do? The f function squares whatever it gets. This is what f gets. This is what f does. So this is called a composition of functions, and order does matter. Now, just for the fun of it, I'm going to write the other one, because we could take them in the opposite order. You always start from the inside, so we're going to let G take his coffee break. What does the result of f of x look like? Well, f of x says x squared is what you get. So what G is going to see is the result of x squared. What does G do? It adds 1 to whatever it gets. It gets x squared, adds 1 to it. Notice that these results are not the same, because x plus 1 squared is x squared plus 2x plus 1. These two are definitely not the same. Going to the g function first, and then f, is not the same as doing the reverse. Keep that in mind. This composition is represented by this small letter. It looks like a degree sign between them. Keep in mind that the one that's going to be closest to the x is the one that gets the x value first. Work from the inside out. Composition of functions. So find each composite function. So first of all, we have f of g of x. So we leave f alone, check on g. What does g do? It takes a number, squares it, and adds 1. So what f is going to see is the result of x squared plus 1. Now what is that? What does f do? F does this. Here's where, remember back in the difference quotient I said, sometimes you just leave blanks where the x's are? Well, to keep from getting confused, this is what f does. F takes 2 times something and subtracts 3 at the end. Well, what did f get? Well, from g, it inherited x squared plus 1. Once you have that down, it's just a matter of simplifying. 2x squared plus 2 minus 3. So f of g of x, alias f composed of g of x, is 2x squared minus 1. Second one, leave the outside function alone temporarily. What is g going to see? It will see what f of x did. Well, f of x takes a number, multiplies it by 2, subtracts 3. That's what g is going to see when f is finished. What does g do? Well, look at g. It squares what it gets and adds 1 at the end. So g of x is going to be, well, this is where we use the parentheses. This is what g looks like. It squares, it adds 1. Well, what does g of x get? G of x gets the 2x minus 3. Now, simplification. G of x equals, first of all, use FOIL on this. We get 4x squared minus 12x plus 9. That's this squared and expanded. And we got a 1 out there. So g of x at the end has 4x squared minus 12x plus 10, or the final result, g of f of x, could be accomplished by just taking this function from the very beginning. This is g composed with f of x. Remember, this is the inside function, that's the outside function. The x goes to the f first, the result goes to the g. And I think this is going to wrap things up pretty quickly here. This is actually 2 lessons, so you have plenty of time to work on this. Inverse function. Now we just talked about the composition of functions, and we saw that this means you take a number, give it to the g function, the result is given to the f function. This one says the x is given to the f function first, the result's given to the g function. Now, an inverse function, that means doing something sort of in reverse or undoing something. Now you got, occasionally, you'll have a function and you'll have its inverse. Since it's sort of the opposite, the way we write it is f minus 1. Now, caution, that does not mean 1 over f of x. This is a special way of writing the minus 1 in what's called superposition. That just means it looks like an exponent, but in this case it's not, because it's referring to a function. Now, for the inverse function, if you've got an inverse function, that means if you take this function and this function and put them together as a composition of functions. One way of doing that is by taking the inverse first and then taking the result through the function itself, the original function. If you do that and you get the original number back, x, and if you do it in the opposite order, give it the function f and then the inverse, and you still get that x back again, then they're inverse operations. You have to check it out both ways. If someone gives you 2 functions and says, okay, check and see whether these are inverse functions. You first have to run through this composition, see if you get x. Run it through the opposite direction, see if you still get x. In other words, this is undoing. So you give this to the inverse, result to this, and you're back to x again. It's sort of like taking a number. We'll just call it x just because that's easy. One thing you can do with that number is you could multiply it by 2. That's a function. But what if you had a second function and its main claim to fame is it multiplies by 1/2? What do you get? You get the original number back that you started with. Not only that, but if you take them in the other order, take the 1/2 x, multiply that by 2. Notice you're doing them in the reverse order, but you still end up with x. your inverses. So how do you find an inverse function? What if you've got a function and you need an inverse for whatever reason? How do you do it? So here we go, and I'll listen to what I'm saying in case some of those lines show up. So what we've got to start with, I'm just going to rewrite it, just as though you saw it in a book somewhere and you were starting on your paper. Step number 1, f of x, remember, is the same thing as writing y. So that's the first thing to do. Copy everything else. All you're doing is writing the y, sorry for the pun, but why are you doing that? Because it's easier to write y than it is f of x a bunch of times. That's one reason. Step number 1. You get the y. Step number 2. What you're going to do is swap the x and the y. What do I mean? Remember, this is your function right now with the y's and the x's. We're going to make every x a y and every y an x. So this becomes, the y becomes an x, and on the right-hand side, we have 2y minus 3. Got that? Just switching the x's and the y's. Very simple. Number 3. If you want a function, what you need is y to be first. So we're going to have to do a little bit of cleanup on this one. If I want to call this something, I want to get 1y. How can I do that? Well, this y that you see here is sort of landlocked inside the square root. We've got to liberate the y. The way to do that is take the square of both sides. So I have x squared because I'm squaring both sides. And on the right-hand side, the square root of something times the square root of something is whatever the inside was to begin with. 2y minus 3. We're getting closer. See the y? We can work with that. I'm going to just swap the two sides, not for any particular reason, but I like it that way. I want the 1y, so I need to get rid of the 3, so I'll add 3 to both sides. I'll have 2y left over here, and the x squared plus the 3 that I just added on this side. But I want 1y, so I'll multiply both sides by 1/2. That'll give me 1y here, and I'll have 1/2 x squared and 3 halves. Almost done. We want the inverse function. We need it to look like an inverse function. Just change the notation, just like we did in the first step. The inverse function is 1/2 x squared plus 3 over 2. And if you wish, I guess I'm going too fast, you could write this as x squared plus 3 over 2. I sort of like this one a little bit better, but that's a personal preference. And last of all, you won't like this one. You really ought to check it. Take the original function, compose it with the inverse function, and see if you end up with x again. That's part one. Part two, you have to do it in the opposite order to make sure you get the same thing. I told you wouldn't like this. Make sure you end up with x that way too. I'm going to leave the algebra with this to you. It's good practice. The better your algebra skills, the better things are going to roll the whole semester. But although I expect you probably know algebra pretty well. But practice makes perfect. If all this works out, you'll be a happy camper without that extra line. Okay, we did all that. There's a picture of this function and its inverse. Now you might think this is a coincidence, but it really isn't. That line in the center is sort of like a folding line. If you look at one of these, either one of these, let's take a look at this curve right here. If this other curve didn't exist, just ignore that for the time being. If you took that y equals x that I had the first arrow on, and you fold the paper or just flip the paper on that axis, you should get the inverse. So if you take this, fold it on the y equals x, it's going to flip over to this one. Or if you take this one, flip it over the y equals x, just like if you're twisting it, you end up with the other side. That's what inverse function looks like. Inverse functions look like when you're pairing them up, looking at them at the same time. There's one beauty, real beauty, of actually using a graphing calculator. You can graph those in seconds. If you've got one of the later versions of the TI-84 Plus, I think it's the Plus where it starts, or a TI Inspire CX or non-CX, you can graph those pretty easily. Graph the first one, imagine what the second one's going to look like. Then graph the second one on the same coordinate system and see how they match up. In fact, what you might want to do is graph this one first, graph this one second, and you might throw in y equals x. See how twisting it along the y equals x takes one and switches it to the other. It can be a fun activity, even if you only do it once or twice. Let the calculator do the work. There's the double check. So if you check it, even just one or two of these, it's a good experience. It doesn't take a whole lot of time. It'll just feel excruciating, but once or twice, it's a good experience. Now, this one says, show that it doesn't have an inverse. Well, let's give it a try. Maybe these people are lying. Let's check it out. So, what am I going to do first? First, I'm going to replace the f of x by y. Second, now remember, this isn't the same equation. This is a new one. The x's become y's and the y's become x's. Very easy. And then you try to switch it so the y is on the left side. Let's see. First of all, I'm going to swap the two sides. That's easy. And then That's supposed to be an x. There we go. Let's subtract 1 from both sides. And then I'll take the square root. That looks like a function. Oops. Ah, wait. When you take the square root, there are 2 answers. So the second one is not a function. If it doesn't have if the inverse isn't a function, it's not an inverse function. Not sure what I said. Anyway, it's not, it has no inverse. There's the original graph. If you take a look at that, it passes the vertical line test, so it's a function, which we knew by just looking at this part, y equals x squared minus 1. We knew it was a function, but looking at the graph, it's a good double check. But when you swap the x and y's, you don't get one. There's a replace, switch the x's and y's, a little bit of work there. There we get the plus and the minus. Because when you square, both those will become just x plus 1's. And at long last, we've ended up with the end of the story. And